Well, we made it, folks. It's Thursday. We're nearly through it. Welcome back, everyone. Any questions at all, folks, before we start today's work? Okay, well, we're getting over the hump of chapter 4. I'd say that's, well, it's kind of a pot shot. Some people feel like L'Hopital's rule is a little bit trickier. I personally feel like optimization was trickier to get through, but we're getting over it. And once we're through these sections, 4.8 is kind of a fun section on Newton's method. We'll look at how to solve really tough equations that you can't normally solve by giving approximate solutions using calculus. Then we'll go over to finding antiderivatives. So we're officially switching over at that stage to the integral calculus, doing everything going the reverse direction in a certain sense. So that's where we're at so far. And just a reminder for upcoming exam, it's still further in the schedule. It's going to be on this week here. So that would be Monday, November 6th. And it's only going to go up to section 4.7. The sample problems are posted and ready to go, and same information down below here. Well, any other questions, folks, before we get started? Okay, well, we left off on a photosynthesis problem, and here's where it ended. It said the rate in milligrams of carbon per cubic meter per hour at which a photosynthesis will take place for some phytoplankton is modeled this way. Here, I is the light intensity, P is the rate of photosynthesis. And we mentioned there is a domain condition on this one. Because it's a light intensity, I ought to be non-negative. So we set it greater than or equal to 0. First thing we chose is first derivative test because the first derivative is tough enough. No reason to go through it twice. The second time would be harder. And after carefully cranking out that second derivative, it ended right here. Next thing we need to get are critical numbers, and we'll run through what we indicated here, the first derivative test. Any questions, folks, before we go to finish off this one? Okay, really at this stage, this is kind of the whole meat of the problem, cranking out that derivative, and doing the algebra to simplify it here to here is not necessarily very easy either. It takes a while to get through that. But once you're here, the rest of the method is pretty fast. We can say, right at this stage, the critical numbers, well, let's maybe back off just a bit. Let's solve the equation set to 0 first, then find the critical numbers, then state them rather. So right here, we have our first derivative. We set it to 0 to get those critical numbers. And from this location, we have one solution, I is positive 2. From this location, we have another critical number, negative 2. But then we need to be a little bit careful on this thing. There's multiple ways to get critical numbers. It's where the derivative is 0, or it's where the derivative doesn't exist. Sometimes we forget to check that condition. I know I do, because lots of derivatives are nice, like right up here. There's no trouble with that first derivative. It always exists everywhere. But if you get something like a fraction, now we need to be suspicious about that thing. We wonder, is there any way that fraction could result in it 0? And if there is, we have to find those values. Those are no new critical numbers in the problem. So let's take a slight pause here and take a look at the denominator and see if we can make it 0. I'm going to use the orange pen just because it's kind of scratch work at this point, but it's something we need to look into. I squared plus I plus 4 is now set to 0. I would try to factor that thing, but there is no way I'm factoring with a positive 4 in a way that the factors multiply to 4 and add to a 1. But doesn't mean there aren't solutions. There still could be a real number solution here. I'm just not seeing a clever way to get it. But we can use the quadratic formula and say If there is a solution, it will be I equals negative b plus or minus the square root of, you have to give this one a more special color. The discriminant here deserves purple. B squared minus 4ac divide by 2a. So quadratic formula is now in effect because that just doesn't look fun to factor. I don't see any great way to do it without trying to find solutions first. And now, before you get too far in the quadratic formula, the first thing you really should calculate is the discriminant. It's going to tell you the nature and the number of the solutions. If our discriminant is a positive real number, you'll get two real number solutions. If it's 0, you'll get exactly one solution. And if it's negative, we get two complex valued solutions. In this class, we throw those away. We're only looking for real valued solutions to our equations. So let's take a look at b squared minus 4ac. The b coefficient goes to the power 1 term, so it's a 1 this time. Minus 4 times the a coefficient is the leading coefficient here, going to that term. It's another 1. And the c coefficient is the constant term of 4. So this becomes negative 16. And in a certain sense, that's great news for us. That means that equation by the red dot has no real number solutions. And so we can pause right here. There's no other way to get a critical number so far. Yes, go ahead. So negative 15 on, oh yeah, that's a negative 15 right there. Must have been focusing on that and forgot our 1. Thanks for spotting that. That's 1 minus 16, so negative 15. Now we can conclude I squared plus I plus 4 equals 0. Scroll just a little bit more. Has no real number solutions. It definitely is solvable, but we're not going to solve it using ordinary real numbers. We need complex valued numbers. So that means these are probably the critical numbers, but we need to look at this really, really intently. That negative 2 is suspicious. We have to remind ourselves I was light intensity. It had a domain condition, and that condition was I has to be positive. So we throw that one away as well. We just have one critical number, as we must. If we're going to find an absolute value, an absolute maximum or an absolute minimum, here we're trying to find an absolute maximum. These new reformulations of both first and second derivative test are emphasizing just one critical number is going to be found. Our critical number, if we're trying to find a maximum, should satisfy this. The derivative will be bigger than 0 for all x less than the critical number. It'll be less than 0 for all x bigger than that one critical number. So coming down here, and now all hinges at this. Let's now finally make the statement. Now that we've done the full analysis on this. Sorry, question first.
Wait, why does the negative 2 not work?
Only because I was the light intensity for the photosynthesis, how strong the lamps are on them. And light intensity could be at lowest 0 for total darkness, and then other positive values.
Okay.
So only because of that reason. Other questions so far? And honestly, going back to that question, that's a really excellent question here. The whole problem hinges on knowing that information. If this was an exam question, the derivative wouldn't be as nasty. It has to be kind of a streamlined question, so we have enough time to do it. But I would probably always also state that, so it's a little bit more clear. We don't have to spend 10 minutes thinking about what's really happening on the problem to get through it. But other questions so far, folks, at the moment? Okay, let's state officially the critical number of, I'll say P, that's the photosynthesis function up above, is I equals 2. We now have a single critical number. We can run this through the first derivative test and see what the results are going to be. So let's go down below just so we can make sure this is all going to fit. We're going to need this, the first derivative. Let me paste that below. And just in case we need it, let's also grab the original function, or let's grab the whole example too, actually. because we need to look at the instructions to decide what does the conclusion even look like for this problem. Okay, so there's our step. Now here's our next step. We made it to step 2 in our organization. First step was just to get a critical number. Now, because we're using the first derivative test, we'll draw a number line. You need to be careful even on this number line. The domain condition is that I is bigger than or equal to 0. So our number line starts like this, right at 0. Next, we put in the critical number of 2 somewhere on this number line. And I'll put an extra symbol here of I, just to remind ourselves, this is the I-axis for light intensity. Now there's 2 regions we have to test from here to here. And we're testing in the first derivative, dp, di. So now let's start plugging in values, getting our test points. And we'll use the increasing, decreasing test first just to see what's happening to the function on those regions. I'd say probably a great test point would be a 1. There's no reason to work super hard. You could put a square root of 2 if you really wanted to as your test point, but 1 does just fine. Over here, 3 is probably the easiest and most sensible value to use. We're plugging these test values right over here. That's the first derivative, dp di. So on the right, I'll put the scratch work of testing. The derivative of p with respect to light intensity, when we're going to plug in 1 first. Light intensity I is set equal to 1 is plug 1 inside of all this, we'll get 100. 2 minus 1, so a value of 1. 2 plus 1 for a value of 3. And the denominator, nothing special is going to happen there. It's always positive because of that power 2, but I'll write it in just so it's clear what's happening. 1 plus 1 plus 4 squared. Well, that whole number has no mention of a negative sign. It's just positive. So I'll go right here. First derivative is positive in this region, but that means it's increasing in that region as well. Now, my guess it's decreasing here, but if I've made a mistake, here's where I'll probably find it. It's a good idea to test it again. So the derivative of p with respect to I, evaluated at I equals 3. Same sort of computation. We'll get 100 here. Nothing happens. That's just positive. But now something does happen here. This will turn into a -1 evaluated at 3. This will be a value of 5. The denominator is positive at 3 squared plus 3 plus 4, all of which is squared. That one negative sign says the whole result is negative. So the first derivative is negative in this region, which implies it's decreasing in that region. So the sketch of this, probably about something like this, right around the critical number of 2, meaning we found an absolute maximum. It's forever increasing from 0 to 2, forever decreasing thereafter. So there could only be one absolute maximum here, no local maximums elsewhere. So let's go and state our conclusion for our step 3. Step 2 is fast because we did all the heavy lifting up here when we calculated the derivative and simplified it. And so far with the instructions for Moodle, we did say we're using the first derivative test, so that's done. We did all of the steps of that test, so step 2 is done. Last thing to do is just to put down a conclusion. Now the conclusion is sometimes tricky because here it says, for what light intensity is P a maximum? They're not asking for the maximum of P, they're asking for I itself. In other words, the lab technician just wants to know what to tune the lamps to. He's not too worried about how much photosynthesis is going to take place. We'll make for our conclusion at I equals 2, and the unit here is thousands of foot candles. I need to Google that one day and figure out how they came up with that as a unit. Such a strange name. So at 2,000 of foot candles, photosynthesis of this phytoplankton is maximized. Meaning we found an absolute maximum, but if you say it in just these kinds of terms, that would be okay for these kind of problems. In fact, if you said at I equals 2, P is maximized, I'd be okay with that because P is in context. It's defined to be that photosynthesis. But sometimes this is just a fancier solution. If you write it out, you'll be able to tell, did it even make sense? Because you're thinking about the context even more. But that's how the process goes. Any questions, folks, with the first derivative test for this one? Okay, what we ought to do is try it again. I have a couple more problems that I think we have just enough time to get through. We're doing this for the homework problems in Moodle, but I'll stop copying it down and checking off those values. So it's just here just as a reminder. And here's the next two problems. There's one pretty similar to this in the homework assignment that we'll be taking a look at. And then with our remaining time, we're going to try to get through example number 4. The fifth example is horrendous. This one's pretty long. I put the solution on it already. I don't think we'll have time to get to this one, but if you like this problem, this is a really good use of the second derivative test, but it also shows why even when you do get to use a second derivative test, it can be a nasty way to go through it in certain problems. But first, let's focus on dealing with this situation right here. So it says a rectangular storage container with an open top is to have a volume of 10 cubic meters. The length of the base is twice the width, and the materials for the base cost $10 per square meters. Materials for the sides cost $6 per square meter, so we're cheaping out on the sides for some reason. We want to find the cost of materials for the cheapest such container. So we're minimizing cost, which definitely from a business standpoint is a reasonable kind of problem for optimization. Here, this one's kind of nasty in a certain sense. The reason I really don't like this problem, if I'm being completely honest, is we have to work hard just to start it off. It's more similar to this one. Excuse me, this one, but building the function was pretty quick. We just formed a constraint, a cubing equation, and substituted. I like these equations because they give you the function right out of the gate and you just work with it. They make better exam questions, maybe with a more tame derivative. But something like this, it's got to be a homework problem because this takes some time to build out the equation that we're going to be optimizing. First thing we can do to start off is we should really build the box so we can organize the information visually to help us out. Got a hair poking my eyeball, sorry about that. So for the box, it says the length of it, the base is twice the width. I'm going to need to use that information, but I'm not going to try to draw it perfectly. I struggled to draw it in the first place. So I'm just going to draw a generic box and put in the information. So the length of the base is twice the width. Let's not worry too much. I'll just kind of draw this rectangle here, another rectangle way out here. You'd be able to see this entire line segment. This is the top of the box. But this line segment from this perspective would be hidden right through here. We should be able to see that whole segment and that whole segment. And so there's our box. We get a little bit better at it every year, but I'm pretty bad at illustrating these things. Next thing we can do is, let's pull in this information. We have a length. Length of the base is twice the width. How about we put L over here just to make it more believable? That's going to be the longer side. We'll call that the width. And that's our height. Now, when it says the length of the base is twice the width, a good choice here is put down X for W. Then the length is twice the width, so 2X would go here. That back up to H. Well, sadly, H is not related to the base in any way by the information they gave us. We need a separate variable. Let's just call it Y. So we have that information so far. And now there's costs of materials. We should look into those costs since we need to put that together to get a cost function. Let's focus on this right here. To start out, it says the material for the base costs $10 per square meter. When it's referring to the base, we're thinking of down here. I'm not too sure if this damages the drawing, but this is what we're thinking of for base. And so, well, it's $10 per square meter. First thing we should find is the actual area of this thing. So we'll say for the base, the area is going to be, we'll just take the width times the length. So it'll be x by 2x. Or a 2x squared. So now that we have the area, we'll just multiply it by $10 per square meter. They'll cancel off the square meters here, and we'll have something in units of just money now. So cost will be $10 multiplying the 2x squared. And so the contribution of cost coming out of the base is the 20x squared here. So the base is done. Now we need to calculate the cost for the sides. But does that make sense to folks so far on our cost for base? Right here, this one should, oh yeah, this one was the volume. I see where you're looking at. Yeah, we'll bring that into when we're going for our constraint equation on this one. But other questions at the moment? Okay, well, let me take off these marks right here so the diagram doesn't get too busy. So now for the sides, we need to calculate area again. And the annoying thing about it is there's two different kinds of areas we have to deal with. This front face and this back face is two different computations we have to put in. And both of them are going to be x, the width of that, and y, the height of that as a rectangular figure. So it's twice x times y to get the front and the back of the box. Putting parentheses just to show where we're plugging in things from each of those dimensions, width, length, and height. Then we go to the other sides. We need the side of this area right here and this area. So this time we'd be using the dimensions of 2x for length and y for height. But there's two faces, the one on the right, the one on the left. So we'll go by plus a 2 first. Then each one of them is going to be a 2x times a y for their areas. And that will be our area for that thing. We need to simplify it and multiply it by, it says material for the sides costs $6 per square meter. So we'll multiply that whole result by 6. First, it's a 2xy plus 4xy. And so altogether, this is becoming 6xy. The total cost is then take $6 per square meter, multiply the prior result for the area, 6xy, and we get 36xy. And I forgot to put my unit here, $sign, just to remind myself we're looking at money at this point. And now we have the total cost of this whole thing. Let me remove these just again so that diagram doesn't look too weird. Now we're ready to develop a function. We could call it f of x if you like. You could call it c of x if you like, to really call it a cost function, and really just up to personal preference. Let's maybe this time, we used an f of x when it was the sum of cubes problem. Let's go with a c of x. C of x will be the cost function. That means we can write down this function finally, and finally officially start this problem. C of x is going to be equal to, first, the cost for the base itself at 20x squared dollars. I'll just write it in as a 20x squared so we can focus on the algebra less than the units. Then 36xy for here. I'll bring back the dollars when we're giving the conclusions. So now that we have all this, we need to pick a test. And we just need to make a decision. How tough is the second derivative going to be? Well, probably extra tough, right? And the first derivative, because there's still a y here. Now's a really good time to go back to what you were mentioning, Stephanie. If we can't differentiate this function, because we never used that information. So let's pull that into the problem. That's where our constraint equation is going to come from. It'll help us to eliminate that y. So we really have an honest function in the variable x and x alone. So let's go over here and put down this is our constraint. Whatever box that we're building, we are insisting on 10 meters cubed. That's what the client wants, I guess you could imagine. So volume must be 10 cubic meters. But now we can go back to the box and just plug in the formula for volume. It's just going to be the product of those three dimensions. So it'll be x times 2x times y is 10. Let's simplify this equation. We now have 2x squared y is 10, and we can now solve for y, eliminating that y right there. So y is now 10 over 2x squared, which means it's 5 over x squared. And anticipating differentiation, let's bring that base x to the numerator. 5x power negative 2 is a much better way to differentiate. There really should not be a quotient rule for these kinds of things. But it's going to plug in right here. And so let's see what happens next. Back to our cost function, we have c of x is 20x squared plus 36x. Now it's multiplied by y through substitution, so we'll plug that in. 5x power negative 2. I'm sensing the need for a calculator all of a sudden, so let me just get one ready to go. I think we just need a basic calculator today. We can make that a little smaller. Okay, so we'll need 5 by 36 and some larger numbers as we go. We got to have a 180 there. And so now finally, our cost function in its simplified form is c of x is 20x squared plus 180. The powers of x combined, when we take x by x power negative 2. Oh, that was 180. I think I was combining my thoughts. X power negative 1 altogether, once we combine bases. So that's the function we're trying to minimize. This is why it's a bad exam question. We wouldn't want to take that much time unless we had like a 2-hour exam or something to get through this. So it makes a great homework question since we have the time to take all these careful steps. Now, once we're here, let's ask the question again. Would you say the second derivative is hard or easy for this function? I agree. We don't have to do any quotient rules, chain rules, product rules. We can differentiate it twice really quickly. Yes, go ahead. So from here to here?
Yeah.
Pretty much all I did was I went right to where this y is and plugged it into that location. And I just carried all this information directly down.
Oh.
Is that what you're asking about, the substitution step? Yeah, so we pretty much just took what was here, got the 5x power negative 2, and just dropped it right into that location. Other questions at the moment? Okay, so now that we have this cost function, we're going to decide on a test, and that's for 2 points, just to say which test we're going to use. Folks correctly said second derivative test is nice on this one. And if you suspect that the second derivative is easy to use, that's going to be probably the better test. So we will, let's recall what we're trying to get to, cheapest. So we're going to minimize, we will minimize c of x using the second derivative test. So now we just go to our cost function, start taking some derivatives. First derivative is going to be important as well, because we also still need a critical number for this kind of problem. So c prime at x, differentiating is going to give us a 40x minus 180. x to the power of -2. So that's a really fast derivative. Next, let's set this equal to 0 and solve that thing. What I would do to solve this equation is eliminate a denominator somehow. You can multiply both sides by x squared if you like, or you could visualize it in this way. You could take 40x, add 180, x power -2 to the right-hand side, then just multiply both sides by x squared. Trying to find a good color for that. I guess let's use sky blue, I guess, why not? So x squared here, x squared here. Now we have 40x cubed equals 180. X power -2 and x squared, they just annihilate, it equals a 1. That's as long as x is not 0. But now that we mentioned x is not 0, we ought to have written that down somewhere. There is a domain condition on this function. X is bigger than 0, only because it's a side length. It couldn't be 0 at all. We have a pretty terrible looking box if it was 0. So we have to think of that as a domain condition when we go through this problem. So now over here, divide by 40. Let's let Desmos do the lifting on that. We have 180 over 40 for a 4.5. Take this cube root of both sides of that equation, and now x equals cube root of 4.5 is the critical number of c of x, our cost function. So now that we have a critical number, we need to take the second derivative and we need to show that that second derivative, no matter what, is always, or minimize, positive. We need a positive second derivative, not just at the critical number, at all numbers x greater than 0. So that's kind of a wild test. Let's take a look at it for just a moment to see how that goes. In the second derivative test, this version here for absolute extreme values, we're looking for a minimum, then the second derivative at x has to be bigger than 0 for all x. It's not talking about the critical number unless you're dealing with a local minimum. Not what we're going for, we want absolute. So now it hinges on, can we prove that the second derivative of this thing, we already have a first derivative, but it needs to always be positive. So let's go to differentiate again. C double prime of x. I'm going to temporarily circle this. That was our first derivative. So the second derivative is, oh, we're on step 2, you could say. We found our critical number. Take second derivative, and right here we'll get 40x, excuse me, just 40. Here we're going to get 360 positive x power -3. So 40 plus 360 x power -3 turns out, only because x itself is positive, this is also positive. You can only plug positive results in here. It has no chance of flipping negative any longer. But if you plotted the whole function doesn't look so great. It's y equals 40 plus 360 x power -3. It can clearly take on negative values, right? But our x itself could never be in this range. X is not negative itself, so you're never going down here. We can now assert that this is, let me put this in a spot that's going to fit and be readable in the notes. It's always positive. Let me drop it a little bit lower. So C double prime at x was 40 plus 360 x power -3. All right, here, it's strictly bigger than 0 for all x, since x is bigger than 0. It's the only reason we're okay here by thinking of the domain of that cost function. That means we have an immediate conclusion, but let's take a look. Did we want the cost, or did we want the side length, or did we want all dimensions, length, width, and height? I have no idea. It's too deep into the problem. Let's remind ourselves, find the cost of materials, the cheapest container. This time we want the actual function value from C of X right here. So you better paste that down just for reference. Oh, actually, it's not too far up there. We can now say for our conclusion, the minimum cost will be C at the critical number, cube root of 4.5. But now we actually have to calculate that cost. You can imagine you're working for a client. If you tell them, well, yes, we can find the minimum cost, but if you don't supply the value, they could be angry with us. So let's now plug all this into a calculator at this stage. So C of X is right over here. We're going to get a decimal answer, but because this is money, we'll just round to the nearest cent on this for a natural answer to the problem. So C of X equals 20x squared plus 180 x power -1. Now that the function is defined, we can take C 4.5 to the power of a cube root would be 1/3 as an exponent. And so this tells us our 10 cubic meter box, who knows what's going in it, but it'll cost $163.54. Client doesn't even want to know the dimensions of that. He just wants it 10 cubic meters in volume as cheap as possible. So who knows what we're sending him, but the side length is that. So $163.54. Yeah, I think that'd be a great way to do that. But you could, if you'd like, kind of just work it out in the ordinary way. If you wrote it out, say this way, C of cube root 4.5. And oh, now the function is kind of out of the way. If you wrote it this way, 20 cube root 4.5 to power 2 plus 180 cube root 4.5, again on this one, to the power of -2, then I would give full credit to an answer that looks like that. We really should toss it into a calculator, but the reason I give full credit is this is absolutely right. And even if you made a mistake on the calculator, you got through the calculus, which is the main drive of the question. So if you went this route, then the other complication is now I have to calculate it by hand instead of using Desmos to define a function. It'll go like this. Let's see if we can get it the same. It should look similar in like a TI-30XA, X2S, where you could put everything in one line. So 24.5 power 1/3 plus 180, we're up to $213. It shouldn't be that expensive. 4.5 to the power 1/3. Now it's $330. Desmos is fun because you can see how far off or close you are as you type. The power of, oh, can I make that a power? I need to put in a power of -2, but it won't let me. That's okay. Exponents multiply, so this -2 will multiply the 1/3 for -2/3. Kind of weird, they won't let you do that though. And it says $99. That doesn't seem right, does it? Oh, thanks for spotting that. So this would be a 2 right here. Definitely more challenging this way for sure, especially if you're doing this on a timed exam. I mean, my fingers would start getting mistyping things out. I would always give this full credit on an exam for sure. $120. Oh no. What did we miss here? Let me take a look at the cost function again. It was power -1. I put power -2 on the writing. Let me try one more time. We're almost getting there. Kind of an adventure sometimes with these problems. Power -1. So this goes back to where it was. $163.54. We got it. Definitely tricky getting it in the calculator. That's a good experience because you never know when you're just going to force to be doing that in a lab or a class. So 163.54. So either way is just fine. Desmos is great because it's pretty rapid, but this is not a bad thing to do either, since we would have to write that on a real exam situation. So thanks for asking that question earlier. Other questions or comments, folks, on getting through this one? Yeah.
So like in this case, our second derivative was nice, it was always positive,
Mhm.
x equals 0. And then we only have one critical number, so like what if it was a problem that had multiple critical numbers and then we weren't sure if our second derivative was positive. But then sometimes if you look at the graph and see that there is an absolute maximum, there's also like little local maximum, and how would that work?
So we wouldn't be able to necessarily use, say, this test if we're not using the second derivative, if we have multiple critical numbers. The same for the second derivative test. If we have multiple critical numbers, then these conditions aren't necessarily going to work out the way we'd like. But we can still put a patch on the problem. Let me put down a graph that kind of captures what you were saying. It would have clearly an absolute maximum, but a local maximum as well. So when you run through this problem, you'll find two critical numbers. Let's call it just C1 for this location. Oh, well, I guess you'd find several, right? C2 and C3. But the problem was finding absolute maximum. The moment you find three critical numbers, we know we have to do some more analysis on this. We'd place the critical numbers on a number line. Let's put, say, C1, C2, C3. Then we'd analyze the problem just like before. This one would have a lot of different intervals to work with. We can say, for example, on the first portion, f prime is bigger than 0. Then across that, it's negative, f prime is less than 0. And now we definitely know we have a problem with the multiple critical numbers, so we probably would look to a graphing utility to get that extra intuition of what's going on in the problem. Once we got a graphing utility available, we'll notice, yes, there is an absolute maximum, and now we will change the function. We're going to allow our function to go like this. We're going to refine the domain to go from 0 to, let's just say, some number b. Then the whole process restarts right here. We can now use the first derivative test on a restricted domain because now we know in that domain there's absolute maximum and the test would work in that location. So if we have a really crazy convoluted situation, we'll have to take multiple looks at critical numbers, the graphs of it, but then we can always settle down to the right region for where absolute maximum would exist. That first derivative would prove it further. But was that kind of the question you were asking about in that situation?
Yeah, so it would just, you wouldn't be able to use the second derivative test.
Exactly. So if you find multiple, we now have to look at the geometry of the problem, the graph, restrict the domain until it's now one critical number again. And so we could say for all x's less than C1 on the restricted domain, derivative is positive. All x's bigger than C1 on the restricted domain, the derivative is negative. So we have an absolute maximum, and we knew that there was an absolute maximum already with that extra look with the graph.
Thank you.
Yep, you betcha. Other questions so far, folks? Oh, I forgot where we're at. We're down here. There we go. Well, we have just one more problem to try to get through. But at this stage, I'd say we hit on pretty much every question that is in the homework. This next one is a little bit tougher, but it's a worthy problem. This one comes from biology. And this is pretty in line with what a biologist might do when using calculus in these kinds of problems. So here's the context. It says, for a fish swimming at speed v relative to the water, let's pause right there and say what v is, because we're going to have to cite these things multiple times. V equals speed of the fish relative to the water, but I'll paraphrase it to that. Notice that the function is stated as E of v. This tells us v is the independent variable. That means it's like the x in the problems. The e itself is like y. So think of v as x as an independent variable. It says next, the energy expenditure per unit time is proportional to v cubed. Well, E is that energy expenditure proportional to V cubed. That's A. A is a proportionality constant. There's the V cubed. So A here is a constant of proportionality. That leaves this. What in the world is that? Let's see. The energy expenditure per unit time. When it said per unit time, they're talking about this. It's proportional to V cubed. That's the A times V cubed. Let's maybe pause right here and see if we can understand what in the world that's saying. We have an expression that goes distance is rate times time. But here we're thinking of distance as being L, the length that, or the distance itself is expressed as L. So length equals rate times time. And so when it says here, per unit time, this quantity is found by solving for T. T equals L divided by R. But now it still leaves the denominator unresolved. We have to figure out how that comes into play. Let's keep on reading through the context. It's believed that migrating fish try to minimize total energy required to swim a fixed distance. And nature does this. Nature is kind of strange in the ways it tries to maximize and minimize processes. That's how a lot of these formulas were even discovered, assuming that they are trying to minimize energy expenditure, maximize caloric intake, that kind of thing. If the fish are swimming against a current U, hey, U came into play, where U is less than V. That's just saying this fish is swimming faster than the current, it's not being swept away. Then the time required to swim a distance, L, is L divided by U minus V. That's the rate. Rate is going to be the speed of the fish minus the speed of the current. And so that's what goes right under here, finally completing that portion. But the reason we walked through all that is because we also need to know that U is a constant. And 0 is less than U. The current is actually moving. U is less than V. The fish is swimming faster than the current, not being swept away. Next, it says the total energy required to swim a distance is given by this equation, where A is a proportionality constant. Determine the value of value of V that will minimize E. So that's our problem so far. And now looking at our constants, it's going to be A, U, and also L, the distance swam that the fish swam. L is equal to distance. Because we said L is a distance, we can also say L is bigger than 0 as a constant. So that constant is positive. The constant U is also positive. The variable V will be positive itself. That leaves just A. And that's where this problem is kind of nasty. A told us nothing about A other than it's a constant in proportionality. My hope is that we can put a sign on it. If we can't, we might not be able to use either the first or the second derivative test until we know if that constant is positive or negative. But looking at all this, V is positive, L is positive, V minus U also positive because V is greater than U from this equation. This is energy expenditure. So if A was negative, we'd be saying the energy expenditure is negative. That means the fish is gaining energy as it swims. That can't be right. It forces our hand into saying A is also positive. So let's say it right here. A is a positive constant as well. Probably that's the only reason they didn't tell us directly, is because we could somehow reason through it, but that's kind of rude. That's a difficult problem already. So aside from all these nasty constants that we had to work about and think through, this could be a typical exam question, just a nicer derivative right here than this one. But now we're ready to work with it. It has a denominator with a variable in the denominator. So for me personally, I would pick the first derivative test in this one. I wouldn't want to bother with a second derivative if I'm doing quotient rule 2 times. So we will minimize E by the first derivative test. So now let's put that into action. Step one is just to take that first derivative. Because they gave us our function in ordinary function notation, not saying e equals, I'll just use Newton's prime notation on this one. But even before doing that, let's rearrange this function. The only reason it's in this format is because they were telling us how they put the function together through that information. So they were talking about proportionality constants and such. But that's not the most convenient form for differentiating. Let's write it this way. Energy expenditure at velocity v for the fish is v right here is the variable. I'm going to take a v cubed, put it in the numerator, but write it this way. A L v cubed. Denominator is v minus u. So my strategy here, when there's so many constants, like in this problem, try to put your constants off to the left. Think of AL as just a glorified number 5, and try to put your independent variable to the right. So that way it's just going to be a better way to organize and remind us as we go which one is variable, which one is constant. Now, when we go to take a derivative of this thing, here's how it goes. E prime at v is first the derivative of the numerator. That's a tough derivative. Anyone see what that would come out as? It'd be a 3v squared, absolutely. But the 3 would also multiply the a and the l to give us that all together. Then it multiplies denominator, v minus u. Then we go minus, copy the numerator, ALV cubed. But now we have to multiply by the derivative of the denominator. That's either 1 or it's -1. Either, anyone see which one it should be? Turns out it's not -1 on this one. And the only reason is when they specify as e of v, it means v is the variable, u is the constant. That's really, really tough, right? This is not a most friendly problem in the world. It's about just dealing with these constants when you can't just throw them away. So this one will turn into a positive one. Then finally down in the denominator, just a v minus u squared. So there's our first derivative. Now what we want to do next is spend quite a lot of time just simplifying the thing so we can get the critical number in a rapid way. So here's what we'll do next. Let's expand 3ALV squared into that group. When it multiplies, it'll just bump up the power of v by 1. So 3ALV cubed. And when it multiplies this way, we're just tacking on the constant u. I'll put that constant u in front of v to not get mixed up. So minus 3ALU v squared. And over here it's times 1, so I'll just copy minus ALV cubed. It's pretty much like the photosynthesis problem at this stage with dealing with the derivative. Denominator is v minus u to power 2. And now let's keep on going with this thing. I have an ALV cubed, 3 ALV cubes. So we have 2 ALV cubes after combining those like terms. And let me just double check. I've combined this one with this one. So 2 ALV cubed, yeah, those are like terms. We just need to record that value. So minus 3 ALU v squared divide by v minus u to power 2. Okay, I think we've got it simplified. We want to simplify it more for equation solving, so that just means factoring essentially at this stage. But any questions so far, folks, to this step of the process? I think the best, it's a greatest common factor for this one. And let's take a look. It's definitely kind of nasty. For greatest common factor, A appears in both, so we can factor out that A. Next, let's see, L does appear in both, so L will get factored out. Good call. You want to pick the smallest power of V that can be factored out. That's the V squared. And let's see, what else is there? I think that's the best we can do for this thing. Does that look about right to folks? Okay, next thing we'll do is, After pulling out ALV squared, visually, this is all you're doing. Take 2AL V cubed, you're dividing it by the greatest common factor, ALV squared. We have cancellations here to here. V squared into V cubed leaves V. So 2V on the first one after factoring at ALV squared. Let me do it again. Minus 3 ALUV squared. So that's the second term. Divide out ALV squared. So A cancels, V cancels. A cancels, L cancels is what I should have said. And V squared cancels. It just leaves minus 3U. So that's our scratch work for getting through that. And that looks like it's final factored form on this. It's degree 1 on the variable V, so I wouldn't want to take it down any farther. And denominator, V minus U squared still. Next, we set that whole thing equal to 0. Actually, let me rewrite it over here because we're going to need that derivative again. Sometimes it's hard to even spot where the derivative is with this much work. So I'm going to set it over here, E prime of V equals 2V minus 3U. Oh, I messed up. Let me get those constants in as well. ALV squared, 2V minus 3U, V minus U squared. So that's our derivative. Now over here, we're looking for critical numbers on that same derivative. So we set it equal to 0 and solve. There's two potential solutions, none of which comes from the denominator, but actually, remember, we have to think of critical numbers for the denominator. Is there a way that the denominator could ever be 0? Yes, if V equals U. However, V exceeds U always, so we're just thrown away from that weird situation. We won't get a critical number from the derivative not existing because the denominator will never be 0 because of the domain of V. So this suddenly became super important right here. Without it, we're stuck and we have multiple critical numbers. We're hoping to get just one. Okay, so nothing from the denominator. We're setting the numerator equal to 0. So it's going to be ALV squared equals 0 or 2V minus 3U equals 0. This is another thing that's challenging about this problem. The moment I write this equation to the right, I need to know what I'm solving for. Are we solving for U or are we solving for V on this thing? Good call. If the variable is V, indicated here, I think that's why they used function notation on this problem. It means we'll solve for V here. So 2V equals 3U, and V is equal to 3/2 of U. If this is all working out, we still have to prove the rest of the steps on the first derivative test. But if it works out, we'll say the fish should swim at a velocity that's 1.5 times the speed of the current to minimize its energy expenditure. Really weird, right? And then they verify experimentally, they in fact do that. Well, let's now go to this equation. Only one way to solve it, V has to be equal to 0. That's alarming. We have two critical numbers. But back up here, V was positive. It's the speed of the fish. If it was 0, that fish is dead and it's getting swept away. So we throw that away and we can say V equals 3/2 of U is the critical number. Now we just have to break down a number line. Let's hide that way down there. And execute the rest of the first derivative test that we indicated. So this would be our step 2. I think we ought to do it down below just to ensure it all fits. On our number line, let me start by going like this. To me, this is one of the more confusing steps. We need to always constantly remind ourselves, what is the variable? It's V, so I want to put V here just as a reminder. And sure, we do know that V is bigger than 0. But if I put 0 here, that turns out to be a mistake. It's kind of weird. Something else goes there. Anyone happen to know what it should be? Let's go back up to that equation. It has to be u, absolutely. The domain of v is all values larger than u. U is unspecified. That's kind of strange because u could be any speed of any current. We're not trying to give a specific value. So this starts at u, right down here. We found a critical number of 3/2 for the value of v. So let's put, 3/2 of u. So 3/2 of u would go right here. Let's zoom back in on that. So here's 3/2 of u. Now we're checking two intervals on the first derivative. E prime at v on this one, E prime at v at this one. That means we're almost done, folks. We just need a couple test values and we'll have a conclusion. Again, this is a weird problem. Anyone see what a test value could be right here? It couldn't be 1 necessarily because here's the trouble. If I put 1 here, I don't know the value of v, so I don't know if 1 is larger than v or smaller than v. It's really, really kind of bizarre in a certain sense. Any other suggestions of something to try for this weird diagram here? Well, we couldn't use v itself necessarily because the v is the thing that's going to vary. We have to put something that doesn't involve v. Absolutely, good call. I mean, already this is 1.5u. We could use, yeah, 1/2 of u. We couldn't put 0.5 of u because that's going to be to the left here. It has to be bigger than u, but less than 1.5 of u. How about like a 1.1 u? Does that sound all right for a test value? It's definitely in between. So here's 1.1 u. Again, that is weird, right? Sometimes for these larger problems, they're not necessarily going to give us a value of u because we want the speed of the current to change from situation to situation. And we want to optimize this for all situations. It's like we're doing a million problems at once.
If you chose 1u, would the equation fail then?
It would, because then you'd be talking about this value. And from right up here, velocity had to be bigger than 1u. Really wild problem. But once we get through this, here's what we'll say next. E prime at 1.1u. Here's our derivative. But remember, it's plugging in for v. V is the independent variable. So this will be equal to AL 1.u squared. That's a positive quantity because of the squaring. We're putting in 1.1u right here. So you multiply by 2 to get 2.2u minus 3u. This quantity is negative. And down below, it's going to stay positive no matter what. We have 1.1u minus u. The power 2 forces positivity on that one. So this whole thing, bigger than 0, we can put, negative, less than 0 on this thing. Let me try again. This is less than 0 because of the 1 negative sign we would get in that location. The derivative here is less than 0. And that means energy expenditure is going down. As the fish speeds up, all the way to here, it levels off. Now, if we could show energy expenditure goes up right here, we have found an absolute minimum of this function. So one more test value. Any volunteers for a value in that region? Good call, 2u does the job on this one. So let's do E prime at 2u. Back up to the derivative, it's AL. Then in place of v squared, 2u goes here, and we square that thing. Right over here where v is, put in 2u, multiplied by 2, and then now it's a 4u minus 3u. But this time that region is, or that factor comes out positive. I'll put in POS for positive, NEG for negative. And we plugged in 2u right here. So this is 2u minus u to the power 2. We didn't divide by 0, so we're in great shape. This whole thing is now bigger than 0. Coming up here, we can say bigger than 0 for the entire region. If the fish swims faster than 150% of the speed of the current, he's wasting energy. Energy expenditure is minimized right exactly here. But it increases the faster and the faster the fish goes. So we're about ready for a conclusion for our step 3. It went decreasing, then increasing for an absolute minimum. Let's see what they want here. The question says, determine the value of V that minimizes E, the energy expenditure. We just want to know how fast should this fish swim, V, to minimize his energy. So let's make this our end conclusion. At V equals 3/2 of U, energy expenditure is minimized. So if that fish is a migratory fish, that's probably what it's trying to do, minimize energy expenditure, swim at that speed. So biology and calculus turns out to be an extremely vast subject. These kinds of questions are not just in isolation. There's an entire discipline, I think it's called bio something, I forget, that goes into the intersection of calculus and biology to answer and think about these kinds of interesting questions. Well, that's where we'll call it a night for today. The next one, Snell's law, is truly nasty, but it's an important formula. It says if a light goes down like this, hits a water, it'll bend. Think of a straw in a cup. It just looks funny. But it turns out what the light is doing is it's minimizing the path to get from A to B as fast as possible. So you could prove that through Snell's law, and Snell's law culminates in this way. So if you're curious about that problem, keep on scrolling down on these notes and the solution is provided down below. It's kind of like what we did with the box. You have to break things down, build a function. This one's kind of nasty, but it's good to see how these go because this is the kind of stuff that gives you all these crazy results in the sciences. Well, that's all we have time for today, folks. Any questions or comments at all? Okay, have a great night, everyone. If you still have other questions, I'll be happy to help out down below. Otherwise, have a great weekend and hopefully try not to shovel snow too much if you don't have to.
Oh, yeah.
That's right.
Hey, question, Dave? Yeah, I'm still starting with the earlier parts. I'm doing much better in the later ones, but for the beginning parts ones, like.
Thank you.
4.1 to 4.3, I'm struggling really a lot in it, but 4.4 and 4.7, I'm doing really
Oh,
well.
awesome. Glad to hear that. Cool. So what's your question on this set?
I don't know how to read the graph. Graphs, right?
So we're looking at, sounds like, oh, it is 4.2, problem number 3. Let's take a look at that.